Hello BC Calc. We are starting 8.2 and we're going to use integrals and area under the curve to connect those three main ideas: position, velocity, and acceleration. A majority of the time you'll be given a graph of velocity or asked to analyze velocity because it's the one in the middle. And if you integrate it or find its area under the curve, you'll get position. So there's a couple different ideas with position, right? There's like the displacement or your net travel. So you could walk forwards and backwards and your net travel would be nothing. You ended up in the same spot. But your total distance traveled would be the absolute value of that. So you wouldn't subtract just because you're going backwards. So there's a couple different ideas here. And we can see here that we have a particle moving along the x-axis. Cool. Position is usually given by x of t. If it was moving along the y-axis, this would just be y of t. And velocity is v of t. Okay, then they give us some information. At t of 2, the particle is located at x equals 5. Cool. So clearly that's not the graph of this. So it says the graph gives the velocity. So this is the velocity graph. And I'm going to label that so we remember that this is v of t. Okay, so what does this mean? This means that above the x-axis, the function is moving in a positive. I guess I'll use green. So this means the function is moving in a positive direction on the x-axis from time is 2 to time is 5. So it's moving to the right. Then at time is 5, the particle changes direction and starts moving left because now the velocity is under the x-axis. And so we have negative velocity, which means we're just moving in a different direction. Okay, so we need to figure out what all this means. Well, where are we getting these numbers from? Here, because we want to do some matching. Let's think about where we're getting these numbers from. This 5 is given to us by the initial position, basically. Since we're starting at time equals 2, that's our initial position, is at 5. And then these other numbers are coming from the area. So if we look and see what the area of each one of these sections is here, the area of this green triangle is 1/2 base times height, so it's 1/2 times 3 times 2. So that gives us an area of 3. And then the area underneath this red triangle, this area is 1/2 times 2 times 2, so that's 2. Those are the areas in there. Okay, so that means that when the particle started, I'll make a little graph here. At time, let's see, we'll do position. Okay, so at the beginning, so at 2 seconds, our function was at position 5, or our particle was at position 5 rather. Okay, then what happened? So over the next 3 seconds, the particle went 3 units to the right. So that means that at time 5 then, the particle was 3 more units to the right. So it's actually at 8. Then what happened next, the particle stopped for just a moment at time is 5 and then started going the other direction to the left, and it traveled 2 units backwards. So where's its position now? It's back to 6. Okay, so we gained 3 units and then we lost 2 units. But the particle still traveled a total of 5 units. It still traveled. It traveled to the right 3 units and then to the left 2 units. Okay, So it moved to the right 3 units, but then went back 2. So it traveled a total of 5 units. Its displacement is only 1. If you walk 3 feet forward and then 2 feet backwards, you're 1 foot in front of your starting point. So your displacement is only 1. Let's think about how we can match these together. All right, the total distance traveled by the particle. The total distance is both positive and negative directions. You're still traveling. So that is our 3 plus 2. That's A. All right, the position of the particle at 7. Time is 7. Well, we know the position is 6. It started at position 5, went 3 units to the right to end up at position 8, then went 2 units left to end up at position 6. So this one is C. And lastly, obviously it's B, but the change in position or the particle's displacement. Well, the particle started at position 5 and ended up at position 6. We can also realize that we have a plus 1 displacement because 3 minus 2 is also 1. Okay, I like this next one because it throws integrals in here. So again, we have a particle. This is just the same particle, but it's just a different way of showing what's happening using integrals. The particle moves along the x-axis so that it's time, da-da-da. Okay, so we can use this to help us out. Anytime you see total distance traveled, that you can't really travel a negative distance. You can travel in a negative direction, but distance means everything is positive. So in math, in order to keep stuff positive, we use absolute value symbols. So when you see absolute value, that's giving you your total distance. We don't care what direction you're going, you know? You can drive to the store and then back home. Your displacement is 0, but you still traveled a total distance of however many miles to get there. Because we don't care that you're traveling north and then south. It doesn't matter. It's an absolute value. So when you see absolute value, that is a total. And then I just wiped those out. But the limits of integration here are telling us, hey, it's our total distance traveled from 2 to 7. When we integrate velocity, we'll get the distance. The absolute value gives us our total distance, not displacement. Okay, position of the particle at t is 7. Let's take a look at just what this means. If we were to integrate from 2 to 7, v of t dt, we have to find the integrand. Well, if we integrate velocity, we'll get this position. And then it's a definite integral, so we have to evaluate it at both 7 and 2 and then subtract them. So what this really equals is our position at 7 minus our position, minus our position at 2. Okay, well, we can rearrange this equation. We did this in the other video. We can add x of 2 to both sides. And we're left with our position at 7 is where we started from, our position at 2, plus our total displacement between 2 and 7. So we rearranged the fundamental theorem of calculus, we rearranged in order to find our position at time is 7. I did that because that's how we get this up here. So this is just using the fundamental theorem of calculus, understanding that when you integrate velocity, you get position, and just doing some basic algebra to both sides. So that's why our position at time is 7 is taking our starting position and then adding our total displacement, where we're ending up at time is 7. Okay, then our last one's B, but the change in position between 2 and 7, we've, discussed this. This is the displacement, right? How much we've changed. So that's this right here before I added x of 2 to both sides. It's telling me how much I've changed. My change in position between time is 2 and time is 7. Change in, right, means to subtract. So that's using the fundamental theorem of calc right here. Please note the difference between B and C. Right, note the difference. This one does not have absolute value symbols, right? It's giving us our change in position. It could be negative, it could be positive, anything, right? Just how we change over that time. This is total distance traveled. It's taking away the ability to be negative. So it's all the distance that we've traveled between these two times. Okay, the next two things that I have for you are just stuff that I found on AP Online that I really liked. Just some practice that I didn't include in what your assignment will be. So for this one, we have, again, the velocity of the particle along the x-axis. Really loving that x-axis movement there. So we're given v of t, and we're given an initial position. Great. Which of the following gives the total distance that the particle travels from time 0 to time 3? Pause the video, see which one you think it is, then we'll go over why. Okay, did you multiple guess correctly? Let's see. It is C. I know that a couple of you probably just put C because, you just did. And hey, you're right, good. Okay, absolute value, so it's either going to be B or C. The word total means that we need that absolute value in there. We don't want to include the 4. We only care about the total distance the particle travels from 0 to 3, like time 0 to time 3. We're already starting at 4. It doesn't matter if our starting point's 1,000,000. We don't need to add it on. It's not how much we're traveling between these two time periods. So that's why our answer is C here. Okay, I feel like this whole video has been really theoretical, and sometimes that makes me nervous. I like to do the math. So this one has us doing some math. Again, we actually have acceleration this time. Whoa. And that means we're probably gonna have to integrate, right? It goes in order, right? If we integrate acceleration, we'll get velocity. If we integrate velocity, we'll get position. Okay. It gives us some info. At time t equals 0, it gives us the velocity. And then at time 0, it gives us the position. So we're going to have to integrate twice because we're asked for the position function. So we're going to have to integrate once with a plus c, then figure out what c is. That'll give us velocity. Then we're going to have to integrate again, plus d, figure out what d is, get the position, figure out at time 2. If you'd like to pause the video and just work through it, see how you did, go ahead. I'm going to just work through it. Okay, so we have a of t equals 12 e to the negative 2t plus 18t. All right, that's my acceleration. So since I have acceleration, actually, let's just write down everything we have. We also know that at time t is 0, the velocity is 2. So we know that the velocity at time 0 is 2. We also know the position of the particle is 4. So I'm going to call position x. So we know that x at time 0 is 4. That's known info, and we'll use that. Okay, if we want to find the velocity, we have to integrate acceleration. So I'm just taking the acceleration function and integrating it. When we integrate this, we know that we're going to have a 12 e to the negative 2t. But then we got to think backwards, like basically we want to take the derivative of this and end up here, right? So we would have had to multiply this by a negative 2. So instead I want to divide it by that. And then this one here, we are going to use our substitution rule for integrating. So it's going to be 18t squared and then also divided by 2. Then we have a plus c. All right, that should be our velocity function. Let's make sure that it is, right? So here, I'll erase this and put -6. And then I'll erase this and put 9 to save space. All right, let's make sure that that works. So I'm just going to derive this quickly in my head, take the derivative, make sure I get acceleration up here. So this is its own derivative. Then we have to multiply by the derivative of the exponent, which is -2. If we multiplied that -6 by -2, you betcha we'd be back to 12. Great. If we took the derivative here, multiply to get 18, take the one less. Okay, great. Plus c. Let's figure out what c is. So we know that when we plug in 0 for t, we'll get 2. And then this will just become 0 up here when we plug it in. And then actually this term goes away. If I plug in 0 here, this term goes completely away. So I'm not going to write it. So we have our plus c. Okay, e to the 0 is just 1, so we have 2 equals -6 plus c, so c is 8. Okay, so our velocity function, v of t, is -6 e to the -2t plus 9t squared plus 8. All right, now I need to get position, so I need to take the integral of this. So if we integrate velocity, we'll get position. All right, this is basically the same idea to integrate, right? So we know we're going to have to divide by a -2 out in front, so we'll get 3e to the -2t. Then we'll get 9 over 3, which is 3t cubed, plus 8t, and then I'm just going to call it d. You could call it c again if you wanted. Okay, we found that. Make sure real quick that it works. If we take the derivative of this, we should get back to our velocity function. And it looks like we would. Great. So next, I'm going to use this information here. So when we plug in 0 for t, we'll get 4 out. So this is 3e to the 0, which is just 1. Then plugging in 0 here, it just goes away. So then we'll just have a plus d. And I'm running out of room, so we'll make it a little smaller. Okay, so d is 1, which means that our position function, our position function x of t is 3e to the -2t plus 3t cubed plus 8t plus 1. Okay, our problem's asking us what's the position at 2. So let's plug in 2. We'll have 3e to the -4. Then if we plug in 2 here, this will give us 8 times 3, which is 24. Then plus 8 times 2, which is 16, plus 1, so plus 17. Yes, I'm picking up my calculator to do 24 plus 17 because I'm tired. Okay, so then I get 41, and I just had like a panic because I didn't see that this was an answer choice. Oh my goodness, thought I did something wrong. No, I didn't know what the answer was before I started. We're just going for it. Okay, so our answer choice, oh my gosh, it's C again, you guys. If you multiple guessed both of those, you would have gotten them right. I think you may be onto something at this point. Okay, nice job. That's basically it. The next slide's gonna show your assignment. All right, your assignment is another AP Online, 8.2, da-da-da, I don't need to read it all out loud. But I'm gonna give you a brain break on Friday, mainly because I need one. But your assignment's gonna be due Monday, March 23rd by noon. You guys have an in-service day that day, like I have to log in and probably do some crap, but you won't have new assignments that day. I'm just making stuff due that day, so like I'm not bombarded on Tuesday with everything. So if you could get this done, it's gonna close on Monday at noon. I would just get it done now, keep it simple. That way you don't have to worry about stuff for like 3 days. So, all right, guys, take care, and I will talk to you soon. Bye-bye.